Okay, chemists, in this lesson we're going to wrap up our kinetics unit and look at factors that affect the rate of reaction, and specifically how we can change what's called the reaction mechanism. First, some vocabulary. A reaction that happens all at once in a single step is called a concerted reaction. But most reactions are stepwise, and they involve multiple steps called elementary steps. And each one is considered to be a concerted step, but you add them together and you get a net reaction. Now, one of those steps is the rate limiting step. It's going to be slower than all the others, and it's going to control how fast the reaction goes. It's kind of like going out with your friends, if there's a bunch of you waiting to meet up and go see a movie together or something, but you're just waiting on that one friend that's always slower than everyone else. No one gets to do anything until they show up. That's how rate limiting steps are. They just make us all wait. But that's one thing that we can look at and becomes the rate of the reaction. And there's a nice trick. The rate law for an elementary step, for an individual concerted step, is based on the coefficients. It's very easy to write rate laws if you know that what you're looking at is an elementary step. And I'll show you what I mean. Let's say we have the overall reaction for the decomposition of peroxide. Peroxide decomposes into water and oxygen. It takes 2 peroxides to give 2 waters and 1 oxygen. And this happens in 2 steps if we do it under catalytic conditions. There's a variety of catalysts that can do this. For example, peroxide, if I react it with sodium iodide, it'll first turn that into sodium hypoiodate and a water molecule. And then that sodium hypoiodate will react with a second peroxide. It'll actually regenerate the sodium iodide, make another water molecule, and that's where your oxygen comes from. So these 2 elementary steps make up a mechanism, and each of them count as an individual step, and then we get our overall reaction down below. That means each step has its own rate law, and I'll call them K1 and K2. And if we know that what we're looking at is a concerted elementary step, which in this case we do, you can write the rate law, R1 and R2, for each step. We do it the same way we did before. It's based on whatever the reactants are in that reaction. So R1 would be based on the concentration of peroxide and the concentration of sodium iodide. And R2 would be based on the concentration of peroxide and the concentration of NaIO. But instead of having unknown orders, let's say A, B, C, D, if we know that these are elementary steps, as long as that's true, whatever the coefficients are for those species in those steps, the coefficients become the orders. So these are all 1 in these examples. So coefficients equal orders in elementary steps. So that's super easy to write the rate law. And then what's the rate for the overall reaction? That's what I really want to know. How fast is this going? Well, we have to know which one of these is running the show. And the slow runs the show. Slow runs the show. That's what happens. So we have to be told which one is slower. And I'm going to tell you that it's this first step. We have ways of figuring that out. That relative to the second step, the first one is the slow one. So that's what's running the show for this reaction. So the overall rate is some constant times peroxide and sodium iodide. That's how fast this particular reaction is going. This should come as a bit of a surprise because you'll notice there's a species in the reaction's rate law which isn't even in the reaction. But if I'm using sodium iodide in this reaction as what's called a catalyst, I'll define that in a second, it actually does affect the rate of the reaction, and we'll even get into more of that later. There's other mechanisms for this reaction, and they would have different rate laws. The rate law is based on what the mechanism is, so I'm just giving you this one as an example. You'll notice that the overall reaction doesn't include sodium iodide. That's because sodium iodide is a catalyst, and catalysts are consumed in an early step, and then they're produced in a later step. And that's what sodium iodide is in this example. So it's a reactant, and then it becomes a product in a later step. These are actually in sequence, step 1 and step 2. What about this NaIO? That also is canceling out from the overall reaction. NaIO happens to be an intermediate, and that's the opposite of a catalyst. That's something that's actually a product in an early step, but it's a consumed reaction in a later step. And you'll notice it's not in the rate law. Intermediates cannot be in the rate law. I'm going to make a note of that. Intermediates can't be in an overall rate law. And there's some tricks called the pre-equilibrium method and the steady state method that we use to replace the concentration of an intermediate with the concentrations of reactants that are proportional. We'll see how to do that at a later time. For now, I'll just mention that we can't leave it in terms of the rate of an intermediate if that otherwise looks like it should be the case. So let's practice this. Now that we've seen what this looks like, let's try this for a hypothetical reaction. Here's nitrogen dioxide and carbon monoxide, and here's what it looks like when they react. By the way, this picture is not just for fun. This actually shows that when you want to make the product, which is a CO2, there's something qualitatively worth knowing, is that the orientation of the molecules actually matters. If you're making a CO2 molecule, the carbon needs to form a bond with the oxygen. That's imperative. I can't rotate this molecule and have what's called an effective collision occur. They actually have to hit each other head on so that the carbon sees the oxygen. That's sometimes something that the AP asks about, and it'll show you pictures like this where you have to choose the right diagram to show that you understand what's being formed. Anyway, back to mechanisms and rate laws. They tell us that the overall reaction has a rate law of KNO2 squared, and it's broken up into 2 steps. The first one is 2 nitrogen dioxides becomes an NO3 and an NO. They want to know what's the second step if there's only 2, and which one is rate limiting. So I'd like you to hit pause and see if you can figure out how you would figure out how to do parts A and B of that problem right in front of you. Okay, let's see how you did. I'm gonna rewrite the overall reaction as we did a moment ago. NO2 plus CO becomes nitric oxide and CO2. That's the overall. And the mechanism is based on the 2 steps. The first step is 2 NO2s becomes an NO3 and an NO. I'm just copying it. And I have to figure out what the rest is. Well, I need to get rid of NO3. It can't be in the net reaction. So my second step must have an NO3 as a reactant. And I also need a CO as a reactant, so there must be a CO reactant somewhere. I'm just figuring out how to add these 2 reactions together. The products, well, I need 1 less NO2, so I'm probably going to produce an NO2, and I'm going to produce a CO2. And now I have something that adds together to give me the net reaction. The NO3 will cancel, and 1 of the NO2s will cancel to give me NO2 plus CO, gives me NO plus CO2. They have to add together to get the net reaction. Now, what's the rate law? Well, the rate of the first one is going to be some first rate constant times the concentration of NO2 raised to its coefficient squared. And the rate of the second step would be K2 times the concentration of those reactants, NO3 and CO, each to the first power. And we're told what the rate law is, so we know that it has to match the rate of the limiting step. That's the first step. So once again, first step equals limiting. That's not always the case, but it happens to be in this example. We could go one further and ask ourselves another question. Was there a catalyst or was there an intermediate in this? Well, there was an intermediate. NO3 was produced and then consumed. There wasn't really a catalyst in this case, unless you consider NO2 a catalyst, which you could. It's sort of autocatalytic because one of the reactants is its own catalyst. We consumed some of it and then produced it later on. So you could argue that NO2 is a catalyst and NO3 is an intermediate. NO3 is definitely an intermediate. Okay, let's wrap up and talk about what these mechanisms look like on an energy diagram and mention a few more things that affect the rate of the reaction. Everyone should know that temperature affects the rate of the reaction, and that's because at higher temperatures, higher temperatures, the word higher is already there, isn't it? At higher temperatures, rates are faster because you have more kinetic energy. Particles are simply moving faster. And they collide with more energy and you get an effective collision. Rates also increase with a higher concentration. Just getting those things closer together causes them to react faster because you increase the frequency of collisions. It's more likely for them to bump into each other. If you picture particles having to collide effectively to react, I want these to have more energy, more kinetic energy, and I want them to be closer to each other. And that's how you do it. You heat them up and you concentrate it. Now we can also speed them up with catalysts. We talked about catalysts today. They do this by changing the mechanism. They give it a completely different pathway. And they lower what's called the activation energy. So let's look at what that looks like on an energy diagram. Let's say I plot how a reaction looks as I start from some arbitrary energy point of reactants to some point of the products. Let's say these are my reactants and these are my products. A mechanism undergoes, if it's concerted, a single energy climb to an energy drop-off. And we have some benchmarks here. This is my energy of the reactants. Here would be my energy of the products. And then what the hurdle is this, this change of where we started to the highest point on the graph. The highest point on the graph down to where we started, that's called the activation energy, E sub A. It's not all the way from the baseline to the top. That's something else. That's actually called the energy of the transition state, which I might as well also mark on here, the energy of the transition state, which is this sort of like high energy complex that's in between the reactants and the products. There actually is an energy change between the reactants and the products, isn't there? As we go from where we started to where we ended. That's delta H. Delta H is E products minus E reactants. And here it's negative, as you can tell, because E products is a smaller number. So what does it look like if we add a catalyst? A catalyst changes the mechanism. It gives us a completely different path. So instead of this single step hurdle, we now have a roller coaster that instead of having only one hill, it's going to have multiple hills, at least two, because you make an intermediate. Catalysts have to give a mechanism with at least more than one step. And we show that by giving a graph that has multiple crests. So I'm going to draw it with a dotted line. And it's going to be lower than the first one, but it's going to have a second energy peak. And we're going to end and start at the same spots, but we are no longer undergoing the same path. This is the catalyzed path. And it has a lower activation energy. It actually has two activation energies. There's also a second one here from this plateau or this trough to this second point, but it's, as you can tell, much smaller. Speaking of that trough in the middle, that's your energy of the intermediate. If you have a pathway with a catalyst, there has to be some kind of intermediate that's produced. And that's what a catalyzed pathway is. Just for fun, you might hear in biology what is called an inhibitor. And an inhibitor is very similar to a catalyst. It just does the opposite. It gives you a pathway that's intentionally slower. Sometimes we want reactions to slow down because they're too fast. So we intentionally add things to make them slower. You still get a new mechanism, you get intermediates, you get different activation energies, but it's now slowed down. Chemists don't always want reactions to be faster. Sometimes we want them to be slower, but catalysts and inhibitors, kind of the same thing, just different definitions based on who speeds things up and who slows things down. All right, one thing to finish this unit up with, which is how the activation energy changes with temperature and is related to the rate constant. We actually said a while ago that rate constants change with temperature. I'm going to show you how. It's with this expression called the Arrhenius relationship. And you should already be going, okay, well, I see an R value. That's familiar, 8.314 joule per mole Kelvin. Temperature in Kelvin, rate constant, there it is, what we've been talking about. What's this Arrhenius constant right here? Well, I'm actually going to get rid of it by showing you a different version of this expression that shows the natural log of the ratio of the rate constants, K1 over K2. Two different rate constants at two different temperatures will be equal to the negative of the activation energy over R times the difference in the inverse absolute temperatures, 1 over T1 minus 1 over T2. This is similar to the Clausius-Clapeyron equation, which we saw in the gases unit. You may not remember it, but it's a very common Arrhenius relationship. And if I plug in my numbers, I get the natural log of 1.1 over 6.4 in this problem is equal to negative activation energy over 8.314 times the difference in Kelvin temperatures, 1 over 823 minus 1 over 898. I get a positive value. Activation energy is always positive. And it turns out to be 140,000, which is 140 kilojoule per mole of this reaction, whatever this reaction is. So that's just a quantitative way to get the activation energy from rate constants and different temperatures of a reaction. That's how we could experimentally get whatever it is for a reaction. That's not on the AP, but you might see it in later chemistry classes. Okay, that wraps up our kinetics unit, looking at mechanisms, how we can define catalysts and intermediates, find the rate law based on a limiting step, and how energy diagrams change as a result of a catalyst.